Hello and welcome to the acid strength tutorial. During this tutorial we review how to determine the relative strengths of given acids. During this tutorial we will use the Bronsted-Lowry definition for an acid, which states that an acid is a substance that donates a proton, H+, to another species. We will do a brief review of acid strength by watching a video on dissociation of strong and weak acids.
This animation demonstrates the difference between a strong acid, hydrochloric acid, and a weak acid, hydrofluoric acid. Click on one of the buttons to see hydrochloric acid, HCl, or hydrofluoric acid, HF, dissolved in water. Hydrochloric acid is a strong acid. Strong acids are strong electrolytes, which for most purposes are assumed to ionize completely in water. In this case, HCl ionizes completely to hydrogen ions, H+, and chloride ions is better represented as hydrochloric acid donating an H+ to water, producing hydronium ion H3O+, and chloride ion. The role of water in this reaction was not shown to simplify the animation. You can think of H+ as a shorthand representation of H3O+. Hydrofluoric acid is a weak acid. Weak acids are weak electrolytes, which only ionize to a limited extent in water. At equilibrium, a hydrofluoric acid solution contains mostly non-ionized acid molecules, HF, and a small amount of hydrogen ions, H+, and the conjugate base ions, F-. This reaction is better represented as hydrofluoric acid donating a proton to water, producing hydronium H3O+, and a fluoride ion. Remember that weak acids only partially ionize in water. The role of water in this reaction was not shown to simplify the animation. You can think of H+ as a shorthand representation of H3O+.
We saw in the video hydrochloric acid, a strong acid, dissociated completely when added to water. There's virtually no HCl left, just H+ and Cl-. Whereas hydrofluoric acid, a weak acid, dissociated only a small amount when added to water. It was primarily still HF with a small amount of H+ and F-. Therefore, the more an acid ionizes, the stronger the acid. For an equilibrium system, we can determine an equilibrium constant, K, with the concentration of products on the top and the concentration of reactants on the bottom. Thus, the reactions with a large K value have more products than reactants, and vice versa. Let's think about this in terms of the general reaction for an acid. In a reaction with a large Ka, there will be mostly products, whereas a reaction with a small Ka value will be mostly reactants. There are a couple things you may want to remember when looking at this Ka equation. One, that H+ and H3O+ are the same thing, and also we do not include H2O in the equation because it is a pure liquid. So when the reactants completely dissociate to the products, there is more products. So in this reaction, there would be a larger numerator, therefore a larger Ka. Using Ka is one of the easiest ways to determine the relative strengths of two acids. But what if we aren't given the Kas for the acids? How do we determine their relative strengths then? To determine the relative strengths of acids based on structure, we will look at the conjugate base of the acid. In an earlier tutorial, we reviewed drawing the conjugate base of a given acid. Now you are asking, how does a conjugate base affect the strength of an acid? The more stable the conjugate base, the more the acid equilibrium will favor the products, or in other words, the more the acid will ionize. Recall that the more an acid ionizes, the stronger the acid. So the more stable the conjugate base, the stronger the acid. We need to go over what will affect the stability of a conjugate base. There are three different things that will affect the conjugate base stability. When comparing acids that have hydrogen bonded to different elements in the same row of the periodic table, we can use electronegativity to help us compare conjugate base stabilities. Remember that electronegativity is how strong the atom attracts electrons in a covalent bond. When we look at the following molecules, we notice that both oxygen and fluorine are in the same row of the periodic table. We will look at the conjugate bases of both of these molecules. Using our knowledge of electronegativity, we know fluorine is more electronegative than oxygen, and therefore fluorine can better accommodate the negative charge, and thus is a more stable conjugate base. Therefore, hydrofluoric acid is a stronger acid than water. Electronegativity can also affect acid strength in another way. For example, consider ethanol and 1-chloroethanol. Which do you think is more acidic? Why? Let's look at their conjugate bases. One anion has a chlorine atom. As chlorine atoms have high electronegativities, they will pull electrons towards them. This will help pull electrons away from the negative oxygen. This will help stabilize the anion, making the 1-chloroethanol the stronger acid. This pull of electrons through single covalent bonds by a nearby electronegative atom is called the inductive effect. When we compare acids that have hydrogen bonded to different elements in the same family, we can use size to compare the relative stabilities of the conjugate bases. We generally use size to compare anions in the same family. Size refers to the number of electron shells, n equals 1, 2, 3. The more electron shells, the larger the atom or ion. As you go down a family, the atoms or ions get bigger. This means there is more room to accommodate an extra electron. We will look at the following molecules to see how this works, and their conjugate bases. The periodic trends show us that as we go down elements in a family, the radius of the chloride ion is larger than the radius for the fluoride ion. The fluoride and chloride ions have the same number of valence electrons, but in the chloride ion, they are able to spread out over a greater area, making the chloride ion more stable than the fluoride ion. Therefore, HCl is the stronger acid. Resonance is another factor that affects the stability of the conjugate base. Please remember that if we can draw resonance structures for a molecule or ion, the real structure is a combination of all the possible resonance structures. Most of the conjugate bases we will look at are anions. The more resonance structures indicates the negative charge is more delocalized, thus helping to stabilize the anion. We will use the following example to demonstrate this. We will look at the conjugate bases of both of these molecules. Both of the ions were formed by losing the hydrogen bonded to the oxygen in the alcohol group. The difference between the two molecules is resonance and electron delocalization. The negative charge on the phenoxide ion is adjacent to the carbon-carbon double bond, and here are the resonance structures that can result from the structure. If drawing resonance structures is difficult for you, you can use the resonance structures tutorial for a quick review. You cannot draw resonance structures for the other anion, cyclohexoxide. Therefore, the phenoxide anion is the more stable conjugate base, which makes the phenol the stronger acid. Alright, I think it's time for you to put those acid strength skills to good use. I will place a couple molecules on the screen. Your job is to pause the video, draw the structures, determine which the strongest acid is, and then play the video to check your answers. So let's get started with the first question. Please pause the video at this time, and good luck. Welcome back. Let's check your answer. We will start by finding the conjugate base of each of the structures. First, we note that in both cases, acidic hydrogen was bonded to an oxygen. However, in the case of the acetate anion, there is another oxygen atom in the ion that can attract electrons and help delocalize the negative charge. This is called the inductive effect. Additionally, for the ethoxide ion, there's no possible resonance structure that can be drawn. The acetate ion, however, has another possible resonance structure, and here are the resonance structures. Therefore, the negative charge is delocalized in the acetate ion, making it the more stable anion, and thus acetic acid is the stronger acid. I have another problem for you to complete. Remember, please pause the video, write down the structures, determine which is the strong acid and which is the weak acid, and then play the video to verify your answer. Here are the structures. Please pause the video at this time, and good luck. Hello again. Let's go over the answers to this question. We'll begin by finding the conjugate base of each molecule. Our three molecules in this question are perchloric acid, chlorous acid, and chloric acid, respectively above. We'll begin by drawing the conjugate bases for each of these acids. In order to find which of these three acids is the strongest acid, we will look at the inductive effect in each of the molecules. In the conjugate base of perchloric acid, because oxygen atoms have a high electronegativity, they have a strong attraction for the electrons they share with chlorine in the covalent bond. As they pull electrons towards them in each of the covalent bonds, they are also effectively pulling electrons away from the oxygen that gained an electron. This will make the conjugate base more stable. Thus, perchloric acid would be the strongest of the three acids because of the inductive effect. Also, because of the inductive effect, chloric acid would be stronger than chlorous acid. And therefore, the next strongest acid would be chloric acid, and the weakest acid would be chlorous acid. We have one more set of molecules for you to use your awesome acid strength skills on. Again, please pause the video, draw the structures, identify the strongest acid, and then play the video again to verify your answers. Here are the structures. Please pause the video at this time, and good luck. Welcome back. For these molecules, we will look at the conjugate bases of each of the structures. In this case, oxygen and sulfur are in the same family, and thus have the same number of valence electrons, but there is a difference between the size in oxygen and sulfur. As sulfur is larger, it can better accommodate the extra electron, and it will be a more stable anion, making H2S the stronger acid. Thank you so much for watching this tutorial. Please feel free to watch the other tutorials, and good luck.